Hi, welcome to this section of the chemistry tutor, and in this section we're going to cover the very important topic of significant figures, or it may be called significant digits in your book. Basically, we're going to be doing a lot of calculations in chemistry, and when you're doing calculations with more than one number, it's really important to look at how accurately each of those numbers in your problem are measured, because your final answer really should be, how many digits you put in your final answer should really be dependent upon what you started with. And so I think the easiest way to really illustrate that and why that's important is from a real world example, not a chemistry example, but just a real world example that we all have some experience with. So we'll do that really quickly, and then I'll give you the rules of significant figures, and then we'll go ahead and do some practice so that you can get the hang of it. It's one of those things really that you can memorize rules all day in the book, but until you sit down and really practice it and count significant figures and get some practice with doing some calculations, you really won't get it until you do that. So I want to definitely spend some time at the end giving you that practice. So this gets some motivation for why this is important. Let's say you're going down the road and you're traveling at some speed, right? What speed is that? Let's just take an example from real life. Let's say your speed in a car or a train or something like that is 10.82 meters per second. This means meters per second. So this means that every single second I am traveling 10.82 meters. So you really need to wrap that in your brain. So another second goes by, another second goes by, another second goes by. Every time a second goes by, I have traveled 10.82 meters. So the fact that I actually have a decimal point here, in other words, I didn't measure this as 10 meters, I didn't measure this as 10.9 meters, I didn't measure this as, 10.82367932 meters, but I measured it as 10.82. And what that means is that I have sort of an implied accuracy to the speed that I'm really traveling. So the train or the car is really going at some speed that's truth. But when I measure it, I have to get a camera out, or I have to get a yardstick, and I have to do my best to judge it. And I only measure it to 2 digits after the decimal point. That's important, so hold that in the back of your mind. Now let's say that I travel this speed for a time, let's say, and the time that I'm traveling at the speed is 2.65427 seconds. All right, so I'm going down 10.82 meters per second, and I'm traveling for 2.65427 seconds. Now, the first thing you should notice is that the accuracy with which I measured my time is much greater. That means that whatever device I used to measure the time, I was able to put more decimals after the decimal point because it was a more accurate representation of the true time. So I'm going down the road, I go at a certain speed, I measure it the best I can, and this is the best I can measure that guy with the measurement tool I have. I click a stopwatch, I see I've gone down the road this many seconds, and I have more decimals because of the way that I'm measuring time. Maybe I have a really good clock or something like that. And so I'm able to put more decimals after the decimal point. So let me now ask you a question. If I'm traveling at this speed and I'm traveling for this many seconds, how do I calculate how far I have traveled? Well, if you think about it, change the numbers to something easier. If I'm going 1 meter per second for 5 seconds, how far have I gone? Well, I just multiply those two numbers. 1 meter every single second, but I'm going for 5 whole seconds, so I multiply those two numbers to give me the distance. How far have I traveled over that time period? So the distance is an example of a calculation that you might actually have to do in real life. Let me change colors here. The distance that I'm going to travel is the velocity times the time, v times t. All right? So if I were going to do that, I would go in my calculator and put 10.82, and I would multiply it by 2.65427, because this is the distance, this is the velocity, meters per second. This is the time in seconds. I multiply it. Now, when I do this, what do I get? Now, in the calculator will give me the following thing. The calculator will give me 28.719214 meters. I'm going to put it in brackets so you can sort of see it stands apart from the number. 28.7192014. Most of us, before we take a chemistry class or a physics class, that would be a perfectly good answer. And we would round the number. Maybe we would round it to 2 or 3 decimal places or whatever. We would just pick a number out of thin air to be able to round that guy. But you should be able to convince yourself that it doesn't really make sense that this is really the true answer, because for the distance that I've traveled. I mean, it's accurate in the sense that the calculator gave us this number, but your answer is only as good as the information you put in. And this guy was only able to be measured to really 2 decimal places after the decimal point, right? So it doesn't really make sense to include 1, 2, 3, 4, 5, 6, 7 decimals after the answer there. It just doesn't really, it doesn't pass the smell test, because if I'm doing a calculation and I measure one quantity really, really accurately, a million decimal places, and then I measure another quantity for the calculation to like 2 decimal places, and I add them or subtract them or divide them or multiply them, it doesn't really make sense. Even though the calculator gives you all those decimals, the calculator is just going to give you numbers. It's just doing math. But to interpret the answer, it doesn't really make sense to take this as a true answer, because when you give this many decimals after the answer, it implies that you really are confident in these numbers, that they're correct. And in fact, they really probably aren't correct, because our velocity was only measured very sort of inaccurately compared to the time. So if you were going to round it, just, you know, without using any real rules of significant digits, but in your head, what would you pick? You might pick, I don't know, let's just do it. 28 point, what makes sense? Let's round to 2, 72. 72 meters. Now, I haven't given you any rules of significant digits yet, but this looks like it might make a little bit of sense, because one of our original numbers has 4 digits in it, really. 2 digits after the decimal. The other guy has a lot more, but when we do the math between them, it makes sense that the final answer should be something with fewer digits in the end there, because it's more representative of what the information we had to begin with is. So this is the concept of significant digits. And I'll just give you one little example. This guy has 4 significant digits. Sig digs, your teacher might call them, but really it's significant digits. So 1, 2, 3, 4. The decimal point has nothing to do with it, really. You just count the digits. And we're going to get into a lot of examples. It gets a little bit more complicated than that, but that's the basic idea. You really in chemistry need to be careful, because everything is being measured. When you measure 5 milliliters of a liquid, when you measure 28.2 grams, 28.2 grams is measured, but if I instead measure 28.2793927 grams, then I'm definitely confident in my measurement in the second hand way, in the second example there, more than just measuring it to 1 decimal place. So when I do a lot of math involving numbers, I really need to be careful that my final answer only has the right number of digits representative of what I put into my problem. And that's what significant digits is all about. So keep that in your mind. It wouldn't make sense to round this to 30 meters. It wouldn't make sense to round it to 29 meters. It wouldn't make sense to round it to 28.729 meters. In this case, it's going to make sense to round it to this. And it's sort of an accepted way to do it that you're going to use all throughout your class. So you need to get comfortable with significant digits. You're going to use it in every calculation there. And it's really intended so that the students, and not only students, but in real life when you're doing real experiments, that your answers kind of make sense based on your input information. All right, so let's talk about how to count significant digits. How do we know how many significant digits do we have in a number? So let me go ahead and title this significant digits. All right, now the strategy here, to be honest with you, is we need to outline what we're doing, and I'm going to put it on the board so that you can see how to count them. And then really what we're going to do is learn how to use this when we do some problems. So you can try to memorize them and hopefully get some information about what I'm going to put on the board here and use it and file it away in your head. But really and truly, you're not going to really nail it home until we do some problems. So the first thing you need to remember when you're doing significant digits, the first thing that you should really be doing is you count the digits. It's pretty simple. Count the digits in the number. All right, so let me give you an example of that. let's say we had the number 23.456. It does not matter that there is a decimal there. All right, so this is 1, 2, 3, 4, 5. Let me go ahead and put it like this, just to make it absolutely clear. This is 5 significant digits. 1, 2, 3, 4, 5. So congratulations, you've already successfully counted significant digits in a real number. So it's not that difficult. What you're really going to be doing most of the time when you're doing the significant digit stuff is just counting the digits in your numbers. The thing you got to be careful about is zeros. That's really the only thing you have to really worry about. When you have digits like this with no zeros in it, it's very simple. You just count the digits. That's the number of significant digits that you have. But when you have a number that has a 0 in it, either before a decimal or after decimal, or we'll talk about it here in a minute, but zero's in the problem, then you need to be a little bit more careful. So let's look at that now. Okay, let's go and say the next little rule. A 0 before a decimal point is not counted. And let me give you an example of that. 0.124. At first glance, you might be tempted to count this and say there's 4 significant digits, but there actually isn't. There's actually 3 significant digits in this guy. Now you might say why? Well, I'm giving you the rule. It's an accepted standard. When there's a 0 in front of a decimal point, you don't count it. The reason you don't count it is because when you think about it, it doesn't really add any accuracy to this number to put a 0 here. In fact, I could actually cover the 0 up and just put 0.124 and it would convey the exact same information. So digits are really only counted in terms of significant digits when they add accuracy, measurement accuracy to a number. In this case, it doesn't, because you know that you can actually cover it up, and if I write down 0.124, you're going to know exactly how accurate I was able to measure that guy as if I had just put the 0 there. The 0 is cosmetic, in other words. It's implied by the decimal point that there's a 0 there. When there's no other number here, it's implied. It's always there, right? So and that's why zeros are a little tricky. Sometimes when you put a 0 in a number, it's actually adding to the accuracy of your measurement. We'll talk about when in a minute. Sometimes when you have a 0 in a number, like right here, it's not really, it's there, but it's not really telling you that the number is any more accurate, because in fact you could eliminate it and it would still mean the same thing. So if there's a 0 and only a 0 before a decimal like this, it's 3 significant figures. I should say it's not counted, so in this case it's 3 significant digits. If I had another digit here, it would be 4 significant digits, and so on. All right, let me go ahead and give you another little rule. Leading zeros to the right of a decimal point are not counted. And again, it's dealing with zeros. So I told you zeros are a little bit special. Let me give you an example of that. What if I have 0.0000223? How many significant digits is this guy? Well, you should know from this rule that this one doesn't count at all. But what I'm telling you with this rule, leading zeros to the right of a decimal. See, these are what we call leading zeros. They're zeros that are before the main digits. But in fact, this guy has 4 significant digits. 1, 2, 3, 4. The reason you do not count these is exactly the same reason as before, because they don't really lend any additional accuracy. I mean, they're basically stuck there to position and tell you how small this number really is. They're placeholders, in other words. They're stuck in there. Yes, they are part of the number. Yes, they have to be there, but they're not really adding to the accuracy. The digits here at the end, this is what the scale or the flask or whatever it is you have, they're telling you how accurate you're able to measure this number. These zeros are just put here because my number is very small. They're placeholders, in other words. Hopefully that makes sense to you. If it doesn't, really you should just memorize it and don't fret too much about it, because you're going to use this so much in chemistry that really you just need to memorize these things. I'm trying to give you a couple of reasons so that hopefully they'll sink in a little bit. But basically, leading zeros before a decimal, don't count them. Leading zeros after a decimal, don't count them. So far, it's pretty easy. Leading zeros before a decimal, leading zeros after decimal, don't count them. Only count the digits. All right, so that's sort of another rule. Now let me give you one more. Trailing zeros after a decimal point are counted. All right, are counted. Let me give you an example of that. 1.2300. How many significant figures does this number have? Well, based on this rule, we have 1, 2, 3, 4, 5 significant digits. Now, you can just memorize the rule, trailing zeros. These are called trailing zeros after a decimal point, right? These are counted. The reason they are counted is because there's some value in having these guys here. In other words, I don't really have to put these zeros here. I can cover them up and just put 1.23. But if I actually go through the trouble of writing these extra zeros here, it means that my scale or my flask or whatever measurement tool I'm using has that much additional accuracy to measure it that much more accurately to stick these two zeros at the end. It's kind of hard to describe other than just telling you that, but these guys are merely placeholders because the number I'm measuring is very small. So these are just used to shift the numbers down over here. These guys are placed here because I'm actually measuring this guy with much greater accuracy. What if I put 10 zeros there? 1.2300000000. Well, I don't have to put those zeros there, but the fact that I do put them there tells me that whatever I'm using to measure this mass or whatever has the precision and the accuracy to be able to pull it off. So they are counted. So let's review the meaning a little bit here. You count your digits, okay, no problem. If you have a zero before a decimal, you don't count it because it's cosmetic. If you have leading zeros after a decimal, you don't count them because they're cosmetic. If you have trailing zeros after a decimal, you do count them. All right? And let me go ahead and tell you here. Let's see here. Just to make it clear, since we're talking about zeros, zeros between other significant digits are counted. All right, let me give you an example of this. What about 702? All right, 702. This is a significant digit. This is a significant digit. This is not a cosmetic number. This is actually part of the number. It's telling me the accuracy with which I've measured this guy is at least to 702. So when I have a zero sandwiched between other numbers, it is counted. So this guy would be 3 significant digits. Okay? Let me give you a couple more rules, and then we will review them. And I know I'm giving you a lot of things to look at, but really it's better to spit it out, and that way you can memorize them and use them rather than guessing. For scientific notation, which you're going to use a lot in this class, only count the digits prior to the power of 10. You know, in significant figures, I should say, scientific notation is always going to have that. So as an example, what if you have 2.43 times 10 to the 6? This is an example of scientific notation, right? 2.43 times 10 to the 6, we talked about that before. How many significant figures does this number have? Well, you don't count the 10 and the 6 is what we're really trying to say. You count these numbers before. So it has 3 significant figures. 3 significant digits. Okay? 3 significant digits. So when you're doing scientific notation, just look at the guys before there and count those guys. That's all you need to do. All right? One more thing I want to talk about is the following. Significant digits only apply to measured quantities, because that's the whole point, right? Talking about measurement accuracy. And this is a very important sentence, so open your ears here. Counted quantities are perfect. In other words, significant figures don't even apply to things that we count, because the whole point of significant figures is based on measurement. You don't want to use too many or too few decimal points in your answer because you're measuring something with a certain accuracy, right? But if you're counting golf balls, or you're counting tires, or you're counting marbles, then significant figures don't really matter, because that's an exact number that you've really picked. So you don't even really even have to deal with that. So a good example would be 2 balls. For significant digits, not applicable. You don't even need to worry about them, I guess is what I'm trying to say. What about 100 coins? Not applicable, all right? Because I've counted out 2 balls. I have 2 exact balls. It's totally exact. There's no point to even talk about significant digits, because I know what the exact answer is. 100 coins. I've counted 100 discrete little coins. I know what the answer is exactly, so that doesn't even matter. And that brings up one final point I'm going to leave you before we work some problems here. This is a number that's an important number. When I have, there's no decimal here, but when I have a significant digit and then zeros that fall after it, these zeros, in this particular case, because I'm counting coins, I told you significant digits don't matter, but what if they're not related to coins? What if I just have 100 of something, 100 grams of something? These 2 digits are, they may be significant and they may not be significant. And I know that even gets uglier, and it's not very pretty to say, but that's the truth. They may or may not be significant, because when you put 2 zeros after it and there's no decimal point here implying accuracy, you don't really know if you measured exactly 100 grams, like exactly, because if I put 100.0, then I would know with total certainty that how accurately, because I have a decimal place, how accurately I measured. But if I measured 100 grams, I mean, who knows? Maybe my scale is really not capable of giving me anything other than, whole numbers of grams. So when you have 100 like this with zeros like that, it gets a little bit ambiguous. So to remove any ambiguity in your answer, sometimes it might be better to represent this in scientific notation, maybe 1.00 times 10 to the 2, if I were talking about grams of something, right? Because if I do that, then going by the rule above, this has 3 significant figures. And what we're going to use this for later is when we do calculations, it's important to know how many significant figures we have in a number, because when we do a calculation, we're going to use that information to choose how many digits are in our final answer. So that's why it's important. So if you have 100 grams of something and you look at this and you're not sure if it's 1 significant digit and you don't count these guys, or if it's 3 significant digits, you're not really sure, it can really affect your final answer, because you might truncate decimals right off the end of your answer without knowing that. So if you're not sure, or if you have any power over it, then you would just write it in terms of scientific notation, and that would tell whoever is looking at this that there's definitely 3 significant figures here. When you look at this guy, since there's a 2, you would be shifting this decimal 2. So these two numbers are exactly the same thing. 100 coins, or 100 grams of something, and 1.00 times 10 to the 2 represents the same thing. It's just that here you're totally clear that it's 3 significant figures, and over here it's really not so clear. But certainly if you're counting things, or if in a book it's like telling you that there are 3 flasks on a table, you're not going to even use significant digits there, because when you're counting objects, those numbers are exactly perfect. All right, what I want to do here is go over these really quickly just to kind of drill them in a little bit. But like I said, you can study rules all day long, but you won't really get comfortable until we actually use them in some calculations. So we're going to do that next. Significant figures. Here's the laundry list of rules. Bottom line is you want to count your digits. Don't care about decimals. They don't even play here. So just count your digits. 1, 2, 3, 4, 5. When they're non-zero, you just count them. 5 significant digits. If you have a decimal, which you're going to have a lot of in this class because you're measuring things, if it's a leading 0 before a decimal, it doesn't count because it's cosmetic. You only count the digits after, right? Now, on the digits afterwards, if you have leading zeros before your significant digits here, you do not count these because, again, they are cosmetic. They're just placeholders to push your number and show you how small of a number you really have. So really, none of these digits count when we count our 4 significant digits here. And if we have a decimal with trailing zeros behind significant digits, they do count because it's implying that my scale or my, my balance or whatever has the required accuracy so that I can measure this out this far. So I do count them. So 5 significant digits here. Now when I have a 0 sandwiched between 2 other numbers, it always counts. It's something you should just remember. It always counts because it's part of the magnitude of the number, which means I'm able to measure it to at least 702, accuracy. So this guy is definitely going to count when you have a 0 sandwiched between numbers like this. When you're using significant digits, which a lot of times in your problems you might have 3.29 times 10 to the minus 2 grams. They might give it to you like that. Well, the significant digits are only counted before the scientific notation part, only this guy. So in this case, 3 significant digits. All of the other rules of zeros and everything apply to this, but you only look before this guy. Finally, when you're counting objects, maybe in some certain problems you may have something that's counted, an exact number. That means it's totally exact. You haven't measured the number of balls with any ambiguity. You know how many balls you have. You know how many coins you have. So you don't even care or factor in the significant digits in your calculation if you've actually counted something like that. But to remove any ambiguity, if you have a number like 100 with some trailing zeros and no decimal point here, maybe you have 300 grams of something, maybe I have 20 grams of something, that 0 there, we're not sure if it's significant, we're not sure if it is significant. So it's better to write it in scientific notation if you have to. And we're going to do an example to show you that in a minute. Now these are the rules that we use to determine how many digits, significant digits a number has. Now we're going to learn some rules to do calculations. And they're not going to be very hard, but we're going to learn them right now. And then we're going to do a lot of examples. So let's go and figure this out now. If you were multiplying and dividing numbers, multiply and divide significant digits, what do you do? All right. Basically, the answer has same number of significant digits as the number in your problem with fewer or fewest significant digits. That's a lot of words. What is it basically saying, to give you a concrete example, is if I'm taking the number 3.4, how many significant digits do I have? 2 significant digits. And I'm multiplying it by something like 1.9876, right? If I do that in my calculator, what I'm going to get is 6.75784. This is the calculator number. But I know that I don't want to keep all those digits because one of my numbers I used to begin with wasn't even measured very accurately. This guy was measured a whole lot more accurately. So how many digits do I keep? Basically, my answer that given by the calculator is given by this guy, and I'm going to keep the same number of significant digits as the number in my problem with the fewest significant digits. In other words, this number has 2 significant digits. Therefore, my answer must have 2 significant digits. So the way I'm going to write that is 6.8. I'm going to round it here because I have a 5 here. This is going to round up to 8, and I'm going to truncate everything right there. 2 significant digits, 2 significant digits. That makes more sense because whatever I'm multiplying here, I was not able to measure this guy nearly as well as I was able to measure this. It doesn't matter how many decimals are after the decimal point. It just matters the total significant digits. 2 significant digits here, 2 significant digits here. All right. Let's go and look, and that's for multiplying and dividing. Let's go and look at the equivalent rule for adding and subtracting. So to add and subtract significant digits. All right. The answer has same number of digits after the decimal point as the number in the problem with the least number of digits after the decimal, with least numbers after the decimal. So this is a little bit different of a rule, all right? So let me give you an example. And then we'll do a ton of examples on the next board here. What if I have 23.997 and I'm going to subtract 18.1? Okay, so I put that in my calculator, 23.997 minus 18.1. What I'm going to get out of my calculator is 5.897. This is from the calculator. All right, but it doesn't really make sense to keep that as my final answer because this guy I was not able to measure nearly as well as this guy. So I need to figure out what to do here. When I'm adding or subtracting, it really matters more what's on the right-hand side of the decimal point. And there's theory behind that and all that, but really the bottom line is it's accepted standard. So, you know, really you should just memorize it. So here, this has 3 significant figures after the decimal. This has 1 significant figure after the decimal. So the answer that I'm going to actually keep is 5.9. I'm going to round this up right here. 5.9 with significant digits because this rounds up and I'm going to only keep 1 digit after the decimal. Notice that this number actually has 5 significant digits. This number has 3 significant digits. But in my answer, I only have 2 significant digits because this is different than multiplying and dividing. I don't really care about the total number of significant digits. I care about what the significant figures are behind the decimal point. That's the difference. So really quick summary, multiplying and dividing, I'm concerned with the total significant figures in both numbers. The answer is going to have the number of significant figures as the smaller number in total. Doesn't matter what's behind the decimal or in front. It's the total number of significant figures driving the answer. This one is different. It only matters how many digits, significant figures I have behind the decimal. Here I have 1 digit behind the decimal, so my answer is going to have 1 digit behind the decimal. I know it's a lot to soak in. You had to learn what significant figures are, why do we care about them, how do you count them, all of the rules, and then when you do calculations involving them, how do you count them in the final answer? What we're going to do now is erase the board and give you several problems really quickly here to give you a good practice and good footing so that you'll get really comfortable with significant figures. And then the good news is, or however you want to look at it, good news, bad news, whatever, when you're doing every problem from here on out in chemistry class, you're going to be doing the significant figures so much that you're not really going to even think about it too much. Once you learn these rules, it's going to be common sense to you really to look. If you have 2 digits here and 4 digits here and you're multiplying them, what do you do? So let's erase the board, work some problems, and give you some practice. Okay, for our first problem, what we want to do is count how many significant figures there are in the number. That's all we're going to do. What about the number 8,008? How many significant figures do we have in that number? Well, obviously this is a significant figure, this is a significant figure. We have these 2 zeros, but they are sandwiched between significant figures. So they count. 1, 2, 3, 4. This has 4 significant digits. Okay? What about 0.00075? How many significant figures do we have here? Well, obviously these count, so there's 2. Leading zeros before a decimal do not count. Leading zeros that come after a decimal but before my other digits, these don't count either. So this is all that counts. It only has 2 significant digits in this number. Okay? What about 0.049300? 0.049300. How many significant figures do I have here? Well, leading zeros do not count. Leading zeros after a decimal do not count. But trailing zeros after a decimal do count. And of course these count, so I have 1, 2, 3, 4, 5 significant digits. 5 significant digits. All right. What if I have 6.02 times 10 to the 5? Right? This could be a measurement in grams, could be a measurement of a volume, could be anything. What do you do here? Well, do you count any of this here? Of course not. You don't count the exponent. You don't count the x, of course. You have 1, 2, 3. 3 significant figures. Notice that in this case, this 0 does count. The reason that that 0 does count is because it's sandwiched between 2 other significant figures like that. All right, so it does count. So 3 significant figures. Okay. E. What about 4.200? 4.200 times 10 to the 5. What do I do here? Well, this counts, this counts. These are trailing zeros, so they also count. 1, 2, 3, 4 significant figures. Okay? What about F? 0.1050. Well, this does not count because it's a leading 0. This is a significant figure. This is a significant figure. The trailing 0 is significant. This 0 is sandwiched between other significant figures, so it also counts. So we have a total of 4. 1, 2, 3, 4. 4 significant digits. All right. And what about G? What if you have 5.00 times 10 to the 9? How many do we have there? Same sort of deal. So we have this counts. Of course, these don't count. After the decimal, they have 2 zeros here, but they do count because they're sort of like trailing zeros, if you can think of it that way. So they have 3 significant digits here. 1, 2, 3. 3 significant digits. So after the decimal, the only reason to even put these zeros here is to show additional accuracy, because really the number can be expressed without them. The fact that we put the decimal and left them in there gives us the additional accuracy. It's telling me that my measurement device is accurately capable of displaying that. So you count them. It's 3 significant digits. Let's do an easier one. 451. How many significant figures do we have? 451 grams of something. 1, 2, 3. 3 significant digits. And what about 0.0169? Again, this does not count. This does not count because it's a leading 0 on the right-hand side. These trailing 3 do count, so we have 3 significant digits. So just wanted to give you a good overview of some example problems that you could see, a smattering of what you might see on your exam, and so, or on your test, or on your homework. So those are just simple significant figure problems. And I'm not gonna lie to you, it does take a little bit of practice to get hang of those zeros. When do they count? When do they don't count? And so just do the best you can. It's really designed to try to prevent you from using way too many digits in an answer. A lot of students, when they first start, they'll put every digit the calculator gives them. Well, those digits at the end don't mean anything, but if your input data only had 2 digits to begin with, that's what we're trying to do here. Give you a good feel for what makes sense. Okay, now we're going to do a few actual arithmetic problems. Let's say we're doing the following calculation. 36.5 minus 2.16 plus 3.452. Now, if you actually put this in a calculator, what you're going to get is 37.792. That's from the calculator. What would be the answer that we would actually circle or write down on our homework? It's not going to be 37.792. That's just too many, especially since a lot of these numbers didn't have that accuracy to begin with. So what do? We're adding and subtracting here, right? So when we add or subtract significant digits like this, we really only care what is after the decimal. The smallest number of significant digits after the decimal. This has 3 significance after the decimal. This has 2 significance after the decimal. This has 1 significant after the decimal. So the final answer is only going to have 1 significant figure after the decimal. 37 point, I'll round this up to 8. This is the number that we're going to pick with our significant digits, 37.8. The reason we pick it is not because this is 3 significant figures in the answer. It's because we're rounding our answer to only have 1 digit after the decimal, because this is the smallest number of digits after any of these decimals in our problem. And that's what we do when we add or subtract. What about 151 plus 4.16 minus 0.0220? What do we do with that? Well, we're adding and subtracting. So if we were going to actually put this in our calculator, the calculator would spit out 155.138, and that's what the calculator would give us. But that's not going to work out. But let's look at what we have here. We have 1, 2, 3 significant figures after the decimal in this number, 2 significant figures after the decimal in this number, and here we actually don't have a decimal at all. So we have basically no significant figures after a decimal. So in that case, we're going to round this guy to 155 and just leave it like that. That's going to be the number that we're going to pick because we don't want to have any significant figures after a decimal point here because this is the least number of significant figures after a decimal. Again, this one had 3 after the decimal, this one had 2 after the decimal, this one had none after the decimal. So our final answer, because we're adding and subtracting, we want 0 significant figures, no significant figures after the decimal. So we just round it accordingly. Okay? I know it may not make sense to you to do this calculation and not put any decimals afterwards, but it really makes sense because the weakest link, so to speak, is this one. We couldn't measure him as accurately for whatever reason. So our final answer, yeah, we have these digits here, and it's pretty to write them all down, yeah, but they don't really give you any confidence that they're correct because this guy didn't have any digits at all after the decimal. All right, now let's do some multiplication. Let's do 265.02 times 0.000581 times 12.18. Now, if we put these all in a calculator and multiply them out, what we will get is 1.875435 and some other digits, and we're going to get this in our calculator, like that. But I think you figured out by now we're not going to actually keep all those digits, but here we're not adding and subtracting, we're multiplying. So what we want to do now is we're not as concerned with what's after the decimal. We're going to look at the total number of significant digits in each one of these guys. This has 1, 2, 3, 4, 5. This does count because he's sandwiched between 2 significant figures. So 1, 2, 3, 4, 5. 5 significant figures, okay? This guy only has 3 significant figures because these zeros here, they're leading zeros behind a decimal, so they don't count. So we have 3 significant figures here, and here we have 4, we just count the digits. So again, 5 significant figures, 3 significant figures total, and 4 significant figures total. We're not looking at what's after the decimal or before, we're counting total significant figures. So the smallest of these is the 3 significant figures here, so we want to round to 3 significant figures, 1.88. This is a 5, so we round this up to 8. We have 3 significant figures in our final answer, and that is the answer. Okay? Let's do one more problem. Let's do 33.58 multiplied by 1.007, and then you take the answer that you get here and you divide it by 0.00705. Okay? So you multiply those guys on top, divide by the number on the bottom, and what you will get is 4796.4624, and then some other digits after that, and this is what the calculator will give you. But you're not going to keep all of those. What we need to do here, because we're multiplying and dividing, we want to look at the total number of significant digits in each one of these numbers. Not what's after the decimal or what's before, like for addition and subtraction, but the total number of significant digits. Here we easily have 4. We can count the 4 here. Here we also have 4, believe it or not. These zeros do count because they're sandwiched between 2 significant figures. 1, 2, 3, 4. All right? And this guy is 3 significant figures. This doesn't count because it's leading 0. This doesn't count because these 2 zeros are leading on the other side here. This 0 does count because it's sandwiched between 2 significant figures. So 1, 2, 3. 3 significant figures. So what we want to try to do is round this guy to 3 significant figures. So let's try to do that. This is the 3rd significant digit. Unfortunately, it's a 9. And this is a 6. So if we try to round up, we're going to get something like 4800 or something. Because it's kind of a ripple effect. This is a 6. So if we try to round this up to a 10, then this is going to go to an 8. Because we're going to round from 79 to 80, basically. So 4800. So you could circle that, and that's sort of the best you can do, but it's a little bit ambiguous how many significant figures are in this number. This is significant, but these 2 here, I mean, we're doing the problem, so I know what we're trying to do here. We're trying to say that at least this guy is significant. But if you just write 4800 down, they're not going to know, did you count 4,800 items? Is it significant at all? Or did you really measure 4,800, in which case they're all significant? In other words, this number is really difficult to write in terms of three significant figures because of the fact that the zeros popped in, and zeros are kind of ambiguous when they're left behind a whole number like that. Something you kind of have to get used to. I know it's a little bit confusing. But the way you get around it, to write your answer down in a bulletproof way that will never get you the wrong answer, is write it in scientific notation. Instead of writing it this way, write it as like this: 4.80 times 10 to the 3. And when you think about it, this is what you're really trying to say, because if you move the decimal 3 spots, 1, 2, and then 1 more, it really is 4,800. It's expressing the same number, but because I write it in scientific notation, this is significant, trailing zeros are significant also after a decimal. So because I write it in terms of scientific notation, all three of these are significant. I have 3 significant digits in our answer, and then there's no ambiguity here when I try to write an answer down like that. So if you ever get into a situation where you're trying to round something up and you really can't round it to the exact number of significant digits that you want, primarily that's going to pop up when you get zeros here, because you're not going to be sure if those are significant or not. Then just turn around and write it in scientific notation. So it's a good idea for you to be comfortable with scientific notation in general, but it's very, very important for that too. All right, I think we're done with this section. We've done quite a bit. It's important. And I could work 25 more problems, but really what we're going to do is get practice doing all this as we go and work problems in the next section and the one after that and the one after that, because we're constantly going to be counting significant figures and writing down the right number of significant figures. The basic idea is you want to count the significant figures in your input numbers so that when you get an answer, you know how many digits to keep. When you're multiplying and dividing significant figures or numbers that you're trying to count these significant figures on, you're going to be more concerned with the total number of significant figures in the input numbers. Whichever one has the smallest number of significant figures, like this guy. This had the smallest number of significant figures, so we wrote our answer to 3 significant figures total. But when you're adding and subtracting, you're more concerned with what lies beyond the decimal point. So this guy has 3 significant figures. This guy has 3 significant figures. This guy has 3 significant figures total. But after this guy, after this implied decimal, I have 0 significant figures. This guy has 2 significance after the decimal, and this guy has 3 significance after the decimal. So since this is the smallest number, I want to keep 0 significant figures after that decimal point. It's a lot to absorb, but as you go through chemistry, you'll find that it gets easier and easier as you do more and more calculations. Review this section as many times as you need to get the hang of it. Plow through the rest of your sections. I promise it will come easier. With that, you'll get your the right answers on your test. And it's really important to get the hang of this, because if you start guessing a lot and getting the wrong number of significant figures, then your teacher's probably going to take off a few points for not including the right number of digits in the answer. It's worth your while to hang on to those points and get the right answer by understanding these rules here.